Okay, in classic style, the Smart Notebook just shut down right in the middle of the video. So we're back now. I did get to finish one example, so I guess I shouldn't complain too much. Okay, so let me extend the page now, see if that works. Oh yeah, look at that. Okay, here's another one. Now, I just want to point out the previous example, we did what we referred to before and now as GCF factoring. Okay, let me show you another one. Okay, and I want to scroll down a little bit more. Okay, here's our function. Again, we're starting out in standard form. And I'm going to end up drawing a graph of this. And just from looking at the standard form, right away, I know my end behavior is like this. And I know my y-intercept is at -8. I can go ahead and put that on the graph if I want. 6, 7, 8. Okay. Now, the last one we factored by using a GCF. Here, when you look at this, there is no GCF. So I can't simplify this at all by factoring out a GCF. There's nothing that all 4 terms have in common. Now, I think I mentioned last time, if you do your factoring for quadratics by grouping method, then this is going to be super easy for you. If you use a different method like the box or, guess and check or something else like that, this is going to seem kind of new to you. But for you guys that already do grouping, this I think will be very obvious to you. So some polynomials, some cubic polynomials, actually very few, but some of the ones you're going to have in your homework, can be factored by grouping. Okay, next class we're going to encounter some that can't be factored by grouping or by GCF, and then we're going to have a whole new set of strategies. But for now, oopsie, I want us just to look at these 4 terms, and we're going to make 2 groups. Okay? Now, within this group, we said earlier we were using GCF factoring. Within this group, there is a GCF. It's x squared. So I'm going to pull that out. X plus 2. Okay? These also have a GCF. The second 2 terms also have a GCF. It's -4. So I'm going to pull that out. Now, the magic happens, and those of you who use this method anyway, the magic happens when you factor those out and you get the exact same thing here in the parentheses. You got to get the same thing in the parentheses for this to work. When you get the same thing in the parentheses, it's almost like now I have 2 terms. This is a term, and this is a term, and I'm asking myself, well, what do those 2 terms have in common? Well, you know what? They both have x plus 2. So I can factor that out to the front. And what's left behind after you factor out x plus 2, you get x squared minus 4. So that's f of x in factored form. Now, again, the cool part here is that I can actually keep going because x squared minus 4 is also factorable. It's x plus 2, x minus 2. That's called the difference of squares. And I can factor that again. Now, here I go. I've got mini equations. To find the zeros, you set this equal to 0, and then you solve the mini equations. X plus 2 equals 0, so x is -2. X plus 2 equals 0, so x is -2 again. X minus 2 equals 0, so x is 2. Okay, so now I can take these solutions. I'm just going to write them out here. -2, I'm going to write it twice just so you remember what happens when you have it twice. -2, -2, and 2. I'll go over and I'll put those on the graph. -2 and 2. Now my end behavior says that from it's going to rise to the right and fall to the left. So from here it's got to go down. From here the graph has to go up. And from our first lesson, or I guess maybe that was, the second lesson, we know that if a root appears twice, like -2 does, -2's on the list twice, that means the graph's going to bounce off of -2. So I know that the graph is going to look something like this. And it's going to come back up like that and go through. Okay. And again, we are going to add one more piece of information to this graph, and that is the relative minimum, right? The maximum, I don't need a calculator or any other tool to figure out that my relative maximum is right here. It's the bounce point at negative 2, 0. But I don't know what this relative minimum point is here. So you would need a calculator to get that. And you would use, calc minimum, and you would be able to find, it'll give you a decimal value, but you know that 0.6666667 is 2/3. So I'm just going to write it as a fraction, negative 9.48. Now again, clearly not to scale, because this says y is negative 9.48, negative 9.5, and I've drawn it right here. So if I want to make my graph a little bit better, yeah, let me make it just a little bit better, because that's pretty crappy. I'm going to bring this down a little bit farther. There's my relative minimum at negative 9.5-ish. Okay? But this bit of information about the relative minimum, I have to use a calculator to get that. I can't get that using algebra. Okay, I'm going to show you one more with factoring by grouping, just because for people who don't normally factor by grouping, that's a new skill. Here's one more. And we'll hope that it doesn't shut down before we're ready. Okay. So again, I can figure out the end behavior and the y-intercept from the standard form. Y-intercept's at 0, negative 4. End behavior, like that. And I can factor this one by grouping. Now don't get too used to factoring by grouping, because it's actually pretty rare to find a polynomial that can be factored by grouping. But just like with quadratics, you should always try to factor it first, right? Because that's the easiest thing to do before you try using quadratic formula or something like that. So I want to try to factor this by grouping. And oh my gosh, miraculously, it's factorable. These two have x squared in common, and I put these in a group. They have negative 1 in common. And again, the magic here happens because, and for those of you who do factoring by grouping, you know that these have to be the same. When those are the same, then I can factor that out to the front. And I find that this is also factorable. It's a difference of squares. X minus 1, x plus 1. If you set each one of these equal to 0 to make a mini equation, you find that the roots are negative 4, 1, and negative 1. And I can take all of that information to my graph. 1, 2, 3, 4. Was it negative 4? Yeah. Negative 4, 1, and negative 1. Those are my zeros. I have a y-intercept that I already figured out. It's at negative 4. I know the end behavior goes down from here and up here. And then it's just a matter really of connecting the dots to figure that out. All right. And maybe, you know what I'm thinking, maybe you want to find the relative min and the relative max before connecting the dots. Wouldn't that be smarter? Yeah, that would be smarter. So go to your calculator, and figure out what the relative min and relative max are, and that will help you make a more reasonable picture, because then you'll put you'll draw it correctly. Again, here I am drawing it not knowing, but I want you now to go to your calculator and figure out what these 2 points are. We can't figure these out algebraically. We have to use the calculator. That's the relative max, and that's the relative minimum. And you can use calc min and calc max. Calc minimum and calc maximum to help you find those. Okay, final thing you're going to do today is to go back to your notes on, and I need to go back a few pages, the notes that we took the first day that we never actually finished because we ran out of time. Let's see if we can do this. No, I want to be over here. These notes is called Classifying Polynomials. And I want to finish up the bottom, which is factoring the sum and the difference of cubes. And a couple people have already kind of asked me about this. Factoring the sum and the difference of cubes. Okay. Now, maybe I should start. I'm actually going to start down here. You don't have to write this down. Just listen for a second. What we're going to factor are expressions like this one. And what's special about them is that this first term is a perfect cube, right? It's x cubed. The second term is also a perfect cube. It's 2 cubed, right? 2 cubed is 8. So a lot of people would think, and I understand why, that this should be easy to factor because you got some perfect cubes. Shouldn't it just be x plus 2, x plus 2, x plus 2? Wouldn't that be awesome if it were just that easy? Well, I want to show you, if I superfoil this out, I'm going to do my superfoiling really quick. X squared plus this becomes 4x plus 4, right? And then I've got to multiply x times every term, so I get x cubed plus 4x squared plus 4x, and then I'll multiply 2 by every term, 2x squared plus 8x plus 8. Okay, and I get x cubed plus 6x squared plus 12x plus 8. Okay, you can see that when you FOIL this out, right, you don't get x cubed plus 8. You get x cubed plus 6x squared plus 12x plus 8. So this is not, this right here, let me get my highlighter and say very clearly, this, and maybe I need like a highlighter, like a red, well, the purple sort of works. This is not the factored form. Okay, it just doesn't work. It doesn't give you, it doesn't become x cubed plus 8. So I want everybody to see that that doesn't work. So when we're factoring these, we have a different sort of method that we're going to use. It's a little more complicated than just x plus 2 times x plus 2 times x plus 2. Okay, so I'm going to write that one down now. Now you should be on your notes. Go to your notes now. I'm going to write that one down here as our first example. That one's, we call that the sum of cubes. And I'm also going to do one that's the difference of cubes. Difference meaning we're subtracting. I'm going to do that one over here. Okay. Now for the sum of cubes, and I hate to say this, but you kind of have to, you got to get this in your brain. Here is sort of the mold that we're going to make these fit into. If you want to factor something where you have two perfect cubes, you get a plus b, a squared, minus ab plus b squared. And maybe I'll use a different color over here. If you want the difference of cubes, you get a cubed. You want to factor something that looks like that, you get a minus b, a squared plus ab plus b squared. And where everybody gets confused is remembering whether you're supposed to use a positive or negative sign in all of these. And someone, I just learned this year, someone just told me this year, you have to remember SOAP. That stands for same, opposite, always positive. Those go together. So this one, this operation is the same, right, as the plus. Opposite, that's this one, always positive. And this one is same here, opposite, always positive. Someone's at the door. I'm going to pause this for a second. Okay, sorry about that. Back to sum and difference of cubes. Okay, so what I do when I look at an expression like x cubed plus 8 is I have to decide within that expression what is a and what is b. So I'm going to jot down, okay, a must be x, right? Because a cubed and x cubed. And b must be 2. Okay? So I'm basically going to make this fit into this mold here, right? So I'm going to put x plus 2. Isn't it nice that the first factor at least is what you thought it was going to be, x plus 2. And then the second factor is a squared, so I need to do x squared minus a times b, so minus 2x, right? And then the last one will be plus 4, because I need b squared as my last term. Okay, now just so you believe it, that this actually works. Now, the other thing is people want to keep going factoring this, right? And I understand why. You should always try to factor it. This is not factorable. There's no factors of 4 that add up to negative 2. So I can't factor that any further. I can check it by superfoiling it. So let me check really quick and make sure I have this right. I'm going to go x cubed, x times negative 2x squared, plus 4x. Then I'll multiply 2 times everything. I'll get plus 2x squared. I'll get minus 4x, and I'll get plus 8. And see what's happening here? These terms are going to cancel out. And I'm left with x cubed plus 8. And it worked. So this is how you factor an expression like x cubed plus 8. Okay? Now looking over at the other one, you might be thinking already like, well, these aren't perfect cubes. You know, 16 is not a perfect cube, neither is 54. But if I factor out a GCF here, I'm going to see 2 perfect cubes, 8x cubed and 27. So again, I'm going to do the same thing. I'm going to look at those numbers. 8x cubed, I'm thinking like, where did that come from, right? It had to come from 2x, right? 2 cubed is 8. X cubed is x cubed. So that came from 2x. And b must be 3, because that's cube root of 27. So again, I'm trying to make this fit into this mold right here. I'm just popping the numbers in. But it's very helpful if you'll actually write out very specifically what a and b are. Okay, so first I need a minus b. So that's 2x minus 3. Now, here's the sticking point. A squared, when I need a squared, I have got to square the whole thing, all of 2x. So this becomes 4x squared, because you have to square the x and you have to square the 2. Very easy to make a mistake there. I need plus a times b, so that's plus 6x. And I need b squared. B is 3, so I need plus 9. Okay, and again, I encourage you to check this by superfoiling it. So I'm going to leave this 2 right here for now. And I'll do 2x times 4x squared, that's 8x squared. And I'll do plus 12x plus 18 minus 12x squared. Oh, I messed up somewhere. I need you guys here. This is hard. 2x cubed, 12x squared, 18x minus 12x squared minus 18x minus 27. And all this stuff here is going to cancel out beautifully. Boom, boom. All those will cancel. And I'm left with 2 times 8x cubed minus 27. Distribute the 2, and you get 16x cubed minus 54. Okay? So that checks out. That works. But this is the factored form. And again, just like the difference of sum of cubes, this part right here is not factorable. I can't go any farther with my factoring on that. Okay? There's a few problems in your homework for you guys to practice at. Okay? And I will see you on Tuesday.